Yeah, that's him, Mr. Adit. You
Halo,
said that you want to meet Alex.
Hello, Alex.
How are you, Adit?
I'm fine.
It's great to hear.
Yeah.
Oke. Selamat pagi Bapak Ibu semuanya dan adik-adik juga ya. Jadi pagi ini kita masih menunggu beberapa peserta yang ingin bergabung dengan kita. Jadi kita akan mulai nanti pukul 9:05. Hello everyone, thank you for joining us, and currently we are still waiting for some participants to join us, and I think we can start at 9:05, I think. Thank you.
Good morning, Pak Edi, Kurniadi. Good morning, Pak Adit, Pak Aditya.
Morning.
Hello.
Morning, Bu Indah.
Yeah, good morning, everyone.
Morning.
Morning.
Welcome.
Morning, Pak Edi. Long time no see you.
Pak Fajar, selamat pagi, Pak.
Selamat pagi, Pak Edi. Good morning, Pak Aditya. Selamat pagi, teman-teman sekalian. Everyone, good morning.
Okay, I think it's good time to start. Okay, thank you. Hello everyone, and before we start our lecture series, please be informed that all participants who have just arrived are kindly requested to mute the microphone. Thank you. Okay, yeah, okay, should be fine. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning and welcome to the Faculty of Mathematics and Natural Sciences Universitas Gadjah Mada, Yogyakarta. Distinguished guests, participants, ladies and gentlemen, Before we explain the event today let us welcome our special invited guests who spare their valuable time to make this event so meaningful for us. His Excellency Dr. Nanang Susyanto, the Governor of Indonesian Mathematical Society, Regional Special Region of Yogyakarta and Central Java, Dr. Igede Aditya Wisnu Wardana, and Dr. Puguh Wahyu Prasetyo, the Vice Chair of Indonesian Algebraic Society, the Head of Departemen Mathematics Universitas Gadjah Mada, Dr. Fajar Adikusumo, Professor Indah Emilia Wijayanti, the Chair of Algebra Laboratory and also the Chair of Organizing Committee for this lecture series, the distinguished speakers, Dr. Rernat Muhammad Fahrani Rashid and Alexander Jimena Balsomo, PhD, and all participants of today's lecture series. Ladies and gentlemen, welcome to the first program of our lecture series on algebraic quantum mechanics. Now, please allow us to give an overview of today's program. First, we will have a speech from the Governor of Indonesian Mathematical Society. First, we will have a speech from the Head of Department of Mathematics. And then the second one is the speech from the Governor of Indonesian Mathematical Society, Regional Yogyakarta and Central Java, and open this program officially. The third one is a photo session. Then we will be arrived in our main agenda. We have two sessions of lectures. The first section will be delivered by Dr. Rernat Muhammad Fahrani Rashid, and the second one will be delivered by Alexander Jimena Balsomo, PhD. And the final agenda are announcements and closing. Ladies and gentlemen, to kick off this morning's program, we would like to invite the Head of Department of Mathematics, Universitas Gadjah Mada, to deliver a speech. To Dr. Fajar Adikusumo, please.
Okay, thank you for the time. And Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good morning, all of you. Good morning, Dr. Alexander Balsomo, PhD. And first of all, I would like to say thanks to the speakers, partnership, Dr. Fahrani Rashid from Department of Physics, Universitas Gadjah Mada. And how are you? Yeah. Okay, and second one, I would like to say thanks to Dr. Alexander Balsomo, PhD, Professor Balsomo, PhD. Sorry for the spelling. From Department of Mathematics, Visayas State University, Philippines. Thanks for accepting our invitation and welcome to UGM virtually.
Thank you.
Because of the condition, and hopefully maybe next time we can visit our university and collaborate with some of our staff for the research. Yeah, hopefully. We would like to say thanks to all of participants and also the Algebra Society and Algebra Group as the organizer of this event. As we know, the quantum mechanics is a theory in physics that study a phenomena in macroscopic, atomic, or subatomic level, which is in general different with the phenomena in classical physics. I think this is a very interesting topic for the lecture today. And the connection between the quantum mechanics and mathematics, which is based on tensor, differential geometry, Lie groups, and some other theories, is also very interesting to learn. This is opening more insight in the application of mathematics and also application in algebra, especially. We hope that this event can provide a new experience for us as mathematicians and trigger a more intense collaborations for research in this field, in this area. And maybe in the future, we can extend our collaboration in some other area of mathematics, not only in algebra, but also in the other field like applied mathematics, computation, and etc. For participants, lastly, I would like to say please enjoy the lectures, and I hope this lecture is very useful for us and giving more more ideas, more inspiration to implement mathematics in the other study. Thank you very much, and wassalamualaikum warahmatullahi wabarakatuh.
Okay, thank you, Dr. Fajar Adikusumo, for the meaningful, great, wonderful, and remarkable speech. And it's now time to have speech from the Governor of Indonesian Mathematical Society, Regional Special Region of Yogyakarta and Central Java. We kindly invite Dr. Nanang Susyanto to deliver speech and to open the program officially. Okay, to Dr. Nanang, please.
Thank you, Isnaini, for the time. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody. First of all, I would like to greet to the guest speakers, Alexander Jimena Balsomo, PhD from the Department of Mathematics, West Visayas State University, Philippines, and also Dr. Ernat Muhammad Farhani Rashid from the Department of Physics, Universitas Gadjah Mada. Thanks for the time, and thanks for fulfilling our invitation. And also the head of Department of Mathematics, Universitas Gadjah Mada, Dr. Fajar Adikusumo, for the hospitality. And also for the committee led by Professor Indah Emilia Wijayanti, and the Vice Chair of Indonesian Algebraic Society, Dr. Igede Aditya Wisnuwardana and Dr. Bogoh Wahyu Prasetyo. Okay, so first of all, I would like to say thank you to the guest speakers. Welcome to Yogyakarta. So let's imagine that you are landing in Yogyakarta and come to the University of Universitas Gadjah Mada in Department of Mathematics. And of course, I would also thank to the Department of Mathematics that is preparing this lecture, especially through its Laboratory of Algebra, and of course for the chair of Laboratory of Algebra, Professor Dr. Indah Emilia Wijayanti. And secondly, for the Indonesian Algebraic Society, that is very, very active in holding scientific activities, especially in region of Yogyakarta and Central Java. So in particular, kind of lecture series like this. And from Indonesian Mathematical Society, region Yogyakarta and Central Java, I would like to say thanks for the collaborations. As we know that during this pandemic, we miss some interaction, face-to-face interactions, but by increasing our intensity in communication and collaboration, hopefully we can still survive. We can still have nice discussion, especially in mathematics and of course in algebra. We also thanks to the university partners in region Yogyakarta and Central Java. Besides UGM, we also have Universitas Diponegoro, Universitas Sanata Dharma, Universitas Ahmad Dahlan, Universitas Islam Sunan Kalijaga, Universitas Islam Negeri Wali Songo, Universitas Negeri Yogyakarta, that also have host some scientific activities supported by Indonesian Algebraic Society and also Indo-MS region Yogyakarta and Central Java. So from Indo-MS, we always support this kind of activities because during this pandemic, we really need collaboration like this. As you know that I always say that, yes, we are in the pandemic situations, and there are dozens of reasons for us to condemn this COVID pandemic, but believe me, there are thousands of reasons that we can take lessons from this pandemic. One of them, we can have a discussion like this easily. So if we formulate mathematically, we move from partial differential equation. So there are constraint of time and space, but there is no space constraints in this pandemic. So it is one of the lessons that we can take from this pandemic. But of course, all of us hope this pandemic will over and we can meet face to face and have a more fruitful discussion. Okay, and today's lecture is very special. As Dr. Fajar Adikusumo said that there will be a quantum mechanic lecture and also learning in like group representation. So I also underlined here is the collaborations. Right, so I refer a quote from Henry Ford. So we know that he is the founder of the Ford Motor Company. It's very famous company. So he says that coming together is a beginning. Staying together is progress, and working together is success. So I hope through this lecture we can, as we know that now we are coming together in this event, in this lecture series, and then next step we can stay together, have a fruitful discussion, and then next step we will have work together, maybe join research or maybe join publication. So that's what we need during this pandemic, and of course after the pandemic, that we hope this pandemic is over. Okay, and maybe some information from Indo-MS, especially from Indo-MS region Yogyakarta and Central Java. So I would report to the president of Indo-MS as well, Professor Indah Emilia Wijayanti. So she is actually the president of the Indo-MS Mathematical Society. We will have 5 Indo-MS schools in region Yogyakarta and Central Java. So first, in the field of algebra, there will be module theory, so basic theory and research development, and it is hosted by Universitas Gadjah Mada. And the next school is related to the mathematical model with GeoGebra. It is hosted by Universitas Sanata Dharma. And the third one is functional analysis and its applications. It is hosted by Universitas Diponegoro and Universitas Negeri 11 Maret, Surakarta. And also introduction to data science with Python. It is hosted by Universitas Sanata Dharma. And the last one is on School in Review Journal. It is hosted by Universitas Ahmad Dahlan. So please go to our website or our Instagram to see to see the detail of this Indo-MS school. And the second one, Universitas Gadjah Mada with IBMS, Indonesian Biomathematical Society, and also supported by the Indo-MS Mathematical Society. We will also host an international conference. It is called ASIMOMath. So it is international conference on biomathematics. So I remember Dr. Alexander said that there is a biomathematics in your university. So please come to our international conference. It will be held on 60 until 70 of July. So next month, and there will be also a workshop on mathematical model in COVID-19. And for foreign students, either for doctoral and magister students, there will be conference grants, including publication fee, and we will announce if you want to if you want to apply this conference grant. And this is the second one, and the last and not least, our agenda is the IICMA. So it is hosted by Indonesian Mathematical Society region of Yogyakarta and Central Java, of course, with the support from Indonesian Mathematical Society and some universities in Yogyakarta and Central Java. We will host CMA International Conference on Mathematics and its Applications. Maybe it will be held around November or December, but the preparation is still under discussion. So please wait, and you can go to our website indomsdiyjateng.org. Okay, maybe I speak too long, so I don't want to take too much time from you. So as requested by the committee, for the sake of development of science, especially in the field of mathematics, officially I open this lecture series on algebraic quantum mechanics. So enjoy this lecture, and hopefully there will be a collaboration after attending this lecture. And trust me, we will go to this pandemic. Hopefully, and then next time we will discuss face to face, and of course enjoy the seminar, enjoy the lecture. Thanks for the attention, and that is, I think, all for me. I will give back the floor to the moderator. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Dr. Nanang, for delivering warm speech and opening the program officially. As mentioned by him, there are some agenda organized by IndoMS. One of them are IndoMS School. And if you are interested in joining them, you can go to IndoMS website and get some more information about them. Okay, the next agenda is a photo session. And may we now ask all invited guests and participants to turn on the camera and pose for group photos, please. So please turn on your camera. It's only maybe take around 2 or 3 minutes, so should be fine. After that, you can turn off your camera. Okay, only few of you who are okay, please, because this is our first program from 3 series. Okay, make sure that you give us a big smile. Still in the morning, right? So it should be okay to give a big smile. Okay, so I will start taking picture in. Okay, some of you still preparing. Okay, maybe I will wait for another 5 seconds. 1, 2, 3, 4, 5. Okay, so okay. I hope you are ready for the photo session. And oh, okay, some of you are okay. Wait. Okay. So please keep your smile. 1, 2, 3. Okay, that's for the first slide. And I go to the second slide. Wait, I save the photos first. Okay, second slide. Okay, 1, 2, 3. Okay, thank you. If you wish to turn off your camera, it's okay right now. Thank you very much for joining the photo session. And now we are arrived in our main agenda. The first session is delivered by Dr. M. Fahrani Rashid. And please let me introduce the first speaker first. Okay. Okay. So our first speaker for today is Dr. Ernad Muhammad Fakhrani Rashid, and he is an associate professor at Universitas Gadjah Mada. He got his bachelor and master from Universitas Gadjah Mada and pursued his PhD from Arnold Sommerfeld Institute für Mathematische Physik, Technische Universität Kassel, Germany. And this is the interesting thing. As mentioned by Dr. Nanang earlier, we have to make some collaborations. So this is why I feel interested. And there is a collaboration from physics and mathematics. So his research interest is related to mathematical physics. And there are some field that he worked in. And no need to prolong this introduction. I think for Dr. Fakhrani Rashid, please. Oh yeah, for the first session, we will have 1 hour. And if you have any question, please write down in chat box. And don't be hesitant if you encounter some difficulties in talking English or in writing in English. Yeah, you also can ask in Bahasa, and then I will help you to translate. That's also fine. And don't forget to write your name and then follow by your question. Okay, for Dr. Fakhrani Rashid.
Okay, thank you very much. I would like to share my screen first. Okay. Have you seen my screen?
Yes, very clear.
Okay. Ya, Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. It is a major honor for me being invited in this lecture as a speaker. Therefore, I would like to thank the committee of the lectures series. Yeah. It is a challenging task for me to introduce quantum mechanics for mathematicians in this very short times, 1 hour. I would like to speak in maybe in mixed mode. Yeah? Sometimes I speak in English and sometimes I speak in Bahasa Indonesia. Okay. However, I have prepared my slides just in English, yeah, systematically. So, who does not understand Bahasa Indonesia can still follow my lecture. Good. My title in this lecture is on quantum mechanics and its mathematical formulation. Good. The first question, yeah, what is quantum mechanics? Yeah, it is relevant, I think, for mathematician, yeah, to ask such question. What is quantum mechanics? Physicists will answer, yeah, that quantum mechanics is a fundamental theory in physics that provides this description of the physical properties of nature at the scale of atoms and subatomic or elementary particles, where classical or Newtonian mechanics fails to provide a description. Good, it is clear, I think. Quantum mechanics is regarded as the generalization of classical mechanics, yeah, in a sense, yeah, because classical mechanics fails to provide the description of such a world, then and quantum mechanics, yeah, is successfully in giving description of subatomics and atomics and subatomics world, then it is understood that quantum mechanics is regarded as a generalization of classical mechanics. Good. It means that classical quantum mechanics can give description of macroscopic system. Yeah, it is hard to answer this question because it is too much a cost, yeah, to apply quantum mechanics in such macroscopic system. Yeah. So in a macroscopic system, classical mechanics still can be applied. Yeah. It will give us easy method, yeah, to solve the problem in a macroscopic system. Now we must understand what is a quantum system. Quantum mechanics apply to physical system, which is called a quantum system. What is quantum system? A quantum system is a physical system. Yeah, when a physical system can be regarded as a quantum system if disturbances, yeah, no matter how small, to the system can not be avoided in any way. Yeah, for example, atoms, yeah, electrons, yeah, elementary particles, and etc. It is a quantum system because in the system, yeah, disturbance, yeah, no matter how small it is, cannot be avoided. Yeah, so it must be take into account in this consideration. Good. Now, I would like to speak about the history of quantum quantum mechanics. Yeah, in the first phase, yeah, we have a primitive old quantum physics. In this time, in this era, Max Planck gave a solution, yeah, in 19. Yeah. To the black body radiation problems, yeah, where classical physics, yeah, classical thermodynamics, etc., yeah, failed to give explanation. And then Albert Einstein proposed the correspondence between energy and frequency in his 1905 yeah, paper, yeah, which explained the photoelectric effects. Yeah, it is. I think this relation is very well known. Yeah? The energy A of a photon, yeah, is equal to h times nu, where h is Planck constant and nu is on the frequency. Yeah. Good. Then some experiment bringing us to yeah, to quantum mechanics. Yeah. For example, quantum effects. Yeah. Frank-Hertz experiment. Yeah. Stern-Gerlach experiment, Davison-Kramer experiment, and Rutherford-Gold foil experiment. The X-ray, alpha ray scattering. Yeah. Good. The next step is the proportion of Louis de Broglie. Yeah. Which is he has extend with particle duality in light, yeah, to particles, postulating that electrons in motion are associated with a wave. Good. Then Werner Heisenberg in 1925, yeah, and Max Born and also Pascual Jordan formulated the so-called matrix mechanics, yeah, the first form of quantum mechanics. Yeah, I think you can open this paper, yeah, the old paper, the first paper of Heisenberg's in this case, in this field, yeah, and Max Born, also Max Born and Heisenberg, and also Pascual Jordan. Good. in about 6 months later, yeah, Schrödinger, yeah, publishes a paper, yeah, titled Quantisierung als Eigenwertproblems. He proposed another form of quantum mechanics, yeah, which is referred to as wave mechanics. Yeah, I'm sorry. Good. And then Dirac and Jordan in 1927, yeah, proposed a transformation theory. It is the generalizations of the Schrödinger wave function and born statistical interpretation of it. It was incorporated into matrix mechanics and the related key number theory of Dirac. Dirac also have proposed another paper, another theory in the same discourse, yeah, i.e. A key number theory, yeah. So this is the paper of Dirac, yeah, Jordan, yeah. So and then it is the mandatory for physics student to read the principles of quantum mechanics. Yeah, this is the form of quantum mechanics, yeah, proposed by P.A.M. Dirac. Now, the first consistent proof of the equivalence between the Schrödinger wave mechanics and Heisenberg's matrix mechanics was given by mathematicians Johann von Neumann in his celebrated books, Mathematische Grundlagen der Quantum Mechanics. So in this book, Johann von Neumann, yeah, then introduce the application of Hilbert space in the formulation of quantum mechanics, and then he has shown that matrix mechanics, yeah, and Schrödinger wave mechanics can be derived from the general form of quantum mechanics, yeah, given in the book of Johann von Neumann. Good. Now I would like to start, yeah, what is quantum mechanics and in detail. Yeah, I would like to choose particular methods in introduce quantum mechanics for you. I call this mechanics, yeah, metamechanics. Yeah. It's mean the common structure of quantum mechanics, classical mechanics, and maybe other mechanics, if exists. Yeah. So it is a common structure. Yeah, we would like a common structure of quantum mechanics and classical mechanics, and then start from this mechanics, and then we would like to discuss the differences of the formulation of quantum mechanics and classical mechanics. Okay, metamechanics, yeah, contains 3 ingredients. Yeah. The first ingredient is physical concepts. It's consisting of states, observables, probabilities, and dynamics. The other is mathematical formulations. It consists of state space, observable algebra, probability measures, curves in the state space. It's the solution of differential equation. Yeah? And the last one is interpretation. This is a philosophical foundation. It consists of interpretation of states, observables, probabilities, dynamics, and etc. Okay, we focus on two ingredients. We focus here on physical concepts and mathematical formulation. Yeah, it is hard to speak about philosophical foundation. Yeah? There is so many discussion about the interpretation of the ingredients of quantum mechanics. Yeah. Good. In physical concepts, yeah, we discuss about states, observables, probability, and dynamics. Physical states. What is a physical state? Yeah. Physical state is something which contains all physical information about the physical system. When the physical system under considerations occupies the state. So when physical system, yeah, occupies or in a state, we are able to gain from the state of all physical information, yeah, in probability, yeah, concerning the physical system. So when a physical system is prepared, yeah, being to be, yeah, prepared to be in states, yeah, so we can get information from the state. Yeah, the information consists of yeah, all physical information. Yeah, the value of observable, yeah, and etc. Yeah, so the physical information. Yeah, what is the physical information we can gain from a state? Yeah, is the value. For example, yeah, the value of physical or mechanical quantities, yeah, or observable, which are relevant to the system. Yeah, okay, all physical mechanical quantities, yeah, the value of all physical mechanical quantities, yeah, of the system, yeah, can be gained from the states, yeah, occupied by the physical system. Good. The next one is physical observable. What is physical observable? A physical quantity which can be measured. Yeah? A physical observable is a physical quantity which can be measured. Yeah? The result of a measurements, yeah, may be a number, a point in space, or etc. The other kind of thing. Yeah? So this is a result of a measurement. The measurement of position, for example, yeah, the measurement of position of a point, a particle in space, yeah, yeah, is a point in that space. Yeah, the point is not a number, yeah? But when we introduce a coordinate system in space, then measurement of the position of a particle in the space can be a triple point. Yeah? When the space, yeah, where the particle exists, yeah, is three-dimensional space. Okay, so here a measurement of the observable, yeah, in this mechanics, yeah, measurement of an observable is regarded as an unfair drawing. So it is unlike rolling a dice or tossing a coin, yeah, in in the roulette, yeah, where rolling dice and tossing a coin is a fair drawing. So in the measurement of an observable in mechanics, yeah, the drawing is unfair. Good. So for every observable, there exists a sample space. Yeah. Because a measurement is regarded as an unfair drawing, then for every observable, there exists, yeah, a sample space corresponding the observable. The result of a measurement is one of the members of the sample space corresponding to the observable as the outcome of the drawing. So The next one is probability. Yeah. The state occupied by a physical system determines a probability on every sample space corresponding to every observable. Okay, let S be a physical system. Furthermore, let S occupy a state psi, and U be a subset of the sample space, sigma O, yeah, corresponding to an observable O. State C, yeah, determines then the probability, yeah, that the outcome of a measurement of the observable O lies in the set U when the observable O is measured. So every state, yeah, system lead to such probability. Yeah. So the probability obtained from the states leads to then to expectancy value and the so-called theoretical uncertainty or standard deviation of the measurement of an observable. I would like to explain what is the theoretical uncertainty. It must be careful here to understand this term. The theoretical uncertainty is understood as the minimum uncertainty which can be obtained from physical measurement by an experimenter. So this is the prediction of uncertainty, yeah, got by an experimenter. Good. Corresponding to every element omega of the sample space, yeah, in sigma O of an observable O, there exist some special states, namely some states sigma omega. This is referred to as special states because it says special feature. Yeah. The probability is equal to 1 if U contains omega, and the probability is equal to 0 if U does not contain omega. Good. Sphere states corresponding to omega will be called eigenstates belonging to omega. Okay. So every member of sample space have some special or eigen states. Yeah. So now the last one, ingredients. Yeah. The last ingredients of physical concept of metamechanics is dynamics. The dynamics of the system describes the evolution of states occupied by the system with respect to time. Yeah. There are two kinds of dynamics. The first one is the dynamics due to disturbances. And the next one, yeah, natural dynamics, smooth evolution of states controlled by the energy, the total energy of the system. So a measurement is an example of disturbance on the system. A measurement causes, yeah, a jump of the system instantly, yeah, after the measurements from the occupied arbitrary states into the eigenstates belonging to the outcomes. So instantly after measurement, the system yeah, is in the eigenstate belonging to the outcome of the measurement. Yeah. There are two descriptions of natural dynamics which are mutually equivalent. Eulerian, yeah, description of dynamics, and the second one is Lagrangian description of dynamics. In Eulerian's description of dynamics, we consider a fixed states, and the dynamics of the system is represented by the time evolution of observable. So you maybe remember the random variable description of stochastic processes. Yeah, it is the evolution of a random variable. Yeah, we regarded the random variable depending on time, and then we get from this description a stochastic differential equation. And second description of dynamics is the Lagrangian's description of dynamics. Yeah, the dynamic of the system in this description is represented by the time evolution of the states, and the observables are kept constant, independent of time. You can remember, maybe in the distributional description of stochastic processes. In this case, we get by Ito formula, we get a Fokker-Planck differential equation controlling the distribution of the random variable. Yeah. Good. There are two such description of dynamics in mechanics. Now we speak about mathematical formulation. Yeah, the first one is a state space. It is the set Ks of all mathematical objects representing possible physical states occupied by a physical system. Okay, the set Ks may have certain structures reflecting the feature of the mechanics and the mechanical system. Yeah. The set Ks may have have algebraic structures like group structure, or topological structure, and also differential structure. So Ks may be differentiable manifolds, and also geometrical structures. Maybe Riemannian geometry or symplectic geometry, and etc. Good. For example, to be mentioned here, a symplectic manifolds. It is a state space for classical mechanics. Poisson manifolds. It is also the state space of classical mechanics in the more general form than symplectic manifolds, and then Hilbert spaces or Wasserstein spaces, etc. It is some example of state space of many kind of mechanics. Good. The last one is the observable algebra. The next one now. I'm sorry. The next one. The next ingredients of mathematical objects, represented physical concepts, is the observable algebra. It is the set OS consisting of all mathematical objects representing physical observables. And the set OS may also have some structure. It is hard to say here because in physics, an observable has a dimension as unit, two different observables with a different dimension, with different units, cannot be summed. So it is hard to say that the sets OS may have some structure. But if we neglected the extent of units of the observable, then the set O S may have some structure. Yeah, good. So for every observable O, there exists a measurable space. Yeah, as I have said in the physical concept. Yeah, when I discussed the physical concept. That is for every observable O, there exists a measurable space, sigma O, comma F, where sigma O is the set of all mathematical objects representing all possible outcomes of measurable measurement of the observable O. And F, yeah, and F is sigma algebra, yeah, appropriate sigma algebra, yeah, mixed by sigma O, yeah, found in sigma O. Good. So the measurable space sigma O, comma F, yeah, represent the sample space of the observable O. Yeah, as I have said that every observable O, yeah, correspond to sample space. The sample space, yeah, is of the form of measurable space. Sigma O, yeah, the possible outcomes of measurement of O, and F is sigma algebra, yeah, found in sigma O. Good. And then the probability, yeah, of the metamechanics, yeah. State psi, yeah, occupied by the physical system, yeah, determines uniquely a probability measure on the sample space, sigma O, comma F, yeah, of every observable O. So let U be an event, yani a member of the sigma algebra F. Yeah. Then POCU is the probability that the outcome of measurements of the observable O lies in the set U when the observable O is measured and the system is prepared in the state psi. It is the probability that the event U happens. Yeah. The probability obtained from the state occupied by the system leads then to the prediction of the expectance value and the so-called theoretical uncertainty, standard deviation, yielded in the measurement of every observable. So for a real random variable X, for example, yeah, defined on the measurable space sigma O F or sample space, yeah, a sample space, the expectation value of X, if given by this formula, yeah, I think it is well-known, yeah, elementary formula, yeah, to obtain the expectancy value of random variable X when, yeah, the probability measure is PO psi. Okay, good. The corresponding theoretical uncertainty delta X psi is given by this formula. Yeah, where the expectancy value of X squared, yeah, in the state, if the system is in the state psi, is given by this Lebesgue integration, yeah, with respect to the probability measure obtained from psi, yeah, determined by psi. Good, especially when sigma O is a set of real numbers. Yeah, this is the subset of R, and X omega is equal to omega. The expectancy value of O, observable O, is given by this formula. And the corresponding theoretical uncertainty, delta O psi, is given by this formula, where O square, the expectancy value of O square is equal to this integration. Good. Let pi be var pi be a member of sigma O, and sigma var pi be an eigenstate belongs to var pi. Yeah. Then sigma pi as eigenstate of var pi leads to Dirac measure. Yeah. So in this metamechanics, every eigenstates of a member of sample space leads or determines Dirac measure. Yeah. With center in the member of sample space. So I think it is elementary. Yeah. It is.
I'm sorry, Pak Rashid, for interrupting. So you have 5 minutes left.
Oh,
time flies so fast.
Surprise. Okay, good. The expectance value of a random variable x and its theoretical uncertainty delta x is given by this formula, and yeah, the value of x in var pi, yeah, and it is important to note that delta x, yeah, the standard deviation of the measurement of x is equal to 0, yeah. And for this special case, yeah, when x omega is equal to omega, we have this, yeah, the measurement of O leads var pi, yeah, and the theoretical expectation of standard deviation is equal to 0. Yeah. Good. Let's make 1 and O2 be two observables. Furthermore, let's omega 1 and omega 2 be a member of sigma O1 and sigma O2 respectively. Yeah. Now let omega 1 and omega 2 have a common eigenstate sigma. If the system is prepared in the common eigenstate sigma, then simultaneous measurements of both observable O1 and O2 will yield certainly omega 1 and omega 2 respectively. Thus, whenever the system is prepared to be in the common eigenstate sigma, both observable O1 and O2 can be measured simultaneously, so that the uncertainties of the measurement of both observable can be reduced to 0. Yeah, good. However, omega 1 and omega 2 may not have a common eigenstate. Yeah, even sigma omega 1 and sigma omega 2 may have no members having a common eigenstate. It is possible. It is happen. Yeah, good. The last one is the dynamics. The natural dynamics of the system in Lagrangian description is represented by a smooth curve C on the state space, which satisfies certain conditions. The curve C describing the dynamics of the system is the solution of an initial problems. And the differential equation involved in the above mentioned initial problems is called the equation of motion of the system. Okay. The equation of motion is determined by the mathematical objects representing a particular observable, namely a mechanical energy of the system. So the mechanical energy of the system plays a particular role in this mechanics. Good. Now I would like to speak to propose or to expose two kind of example of metamechanics. The first one is classical mechanics, and then we discuss about the quantum mechanics. In classical Newtonian mechanics, state space is given by, for example, symplectic manifolds, or Poisson manifolds. A point in the state space represents a general momentum and the general position of the system. The observable algebra is given as the set C infinite M of all real smooth functions defined on the state space. A classical observable is represented as a function which depends on general momentum and general position of the system. And the symplectic structure omega of the Poisson structure lambda leads to the so-called Poisson brackets in the C infinite M. The sample space of the classical observable A is the range of A accompanied by a sigma algebra F inherited from the Borel sigma algebra in the set of all real numbers. Good. If the system is in the states represented by a point M in the state space M, then the expectation value of a measurement of a classical observable A is given by a value AM of A as a function of M, and the theoretical standard deviation delta AM of the measurement of A is 0. It means that the experimenter in classical mechanics can reduce the uncertainty of her or his measurement as small as possible, yeah, by improving her or his methods as well as her or his apparatus. Thus, in classical mechanics, the uncertainty of a measurement is the matter of experimenter, their methods, their apparatus, or etc. Good. Again, let's the system is P in the state M. Then the state M leads to a probability measure on the sample space, yeah, in the form of a Dirac measure, D A centered at DAM. Yeah. Good. If P is another classical observable, then the state M leads to the probability Dirac measure, DBM. Yeah. Good. All states are eigenstate for all observable. Yeah. Therefore, it is possible that every two classical observables can be measured simultaneously with zero uncertainties. So the dynamics of classical mechanics, yeah, are controlled by the so-called Hamiltonian equation. It is the form of Hamiltonian equation in symplectic manifold. The Hamiltonian function H represents the total mechanical energy of the mechanical system. Xh is the Hamiltonian vector field on M generated by H. Okay. Locally, yeah, the above equation can be written as this equation, yeah, and where 2n is the dimension of the manifold M, and P alpha is a local canonical coordinate system on M. The solution of the above Hamiltonian equation, together with initial values, is a smooth curve on M, describing the evolution of the dynamical system. The rate of the change of the value of an observable A is given by this equation, where this is a Poisson brackets given by determined by the symplectic structure. Good. Now, quantum mechanics. The standard state space of this mechanic is a separable infinite dimensional complex Hilbert space. Yeah. The quantum state is represented by one-dimensional subspace called ray in the Hilbert space. Yeah, it is standard formulation, yeah, of quantum mechanics. This means that the correspondence between states and vectors in the Hilbert space is not one-to-one. In calculation, a state is represented by a unit or normalized vector in the corresponding ray. Two normalized vector psi and phi in H, with psi is equal to A times phi, where A is a complex number corresponding to the state, correspond to the same state. Yeah. Since Hilbert space H is a vector space which is closed under vector addition, the vector addition in the space leads to the concept of superposition of states. Yani, two states can be summed, yielding another state. No such superposition of states is found in classical mechanics, because in classical mechanics, the space is not does not have linear space structure. But if the system is prepared to be in state psi, it is possible that the system also to be in another states, because the state psi can be written as a superposition or summation of other states. Such feature is also not found in classical mechanics. So then observable algebra. An observable O is represented in this quantum mechanics by a complete self-adjoint linear operator O acting in the Hilbert space H. The sample space of this observable O is formally constructed from the set XO of all eigenvalues of operator O. Yeah. So that the operator O representing an observable O is self-adjoint implies that all eigenvalues of O are real, and eigenvalue subspace are mutually orthogonal. That the operator O representing an observable O is complete, yeah, implies that the Hilbert space H can be written as a direct sum of all eigenvalue subspace corresponding to XO. An orthonormal basis can be, therefore, an orthonormal basis can be constructed from orthonormal basis on each eigenvalue subspace. Every vector in Hilbert space H can be written as a Fourier series, yeah, with respect to the orthonormal basis consisting of eigenvectors of the operator O. There are some observables whose sample space are a priori imposed from the beginning. Yeah? For example, the coordinate of the position on the components of the linear momentum. Yeah, and it is an uncountable subset of the real lines. In this case, the orthonormality means that delta Dirac's orthonormality. In all cases, the Hilbert space H is isometric or isometric isomorphic to the space, Lebesgue space, yeah, L square IO mu, where mu is depend on XO, yeah, where mu is the counting measure if XO is countable, and it is the Lebesgue measure if XO is uncountable. So the probability, yeah, let the quantum system be in state psi. The probability measured P psi determined by the state C on the sample space XOF is given by this formula. Good. Yeah. And for every multiple set U in sigma algebra F, where phi omega is a normalized eigenvector belonging to psi omega. Sorry. The expectance value and theoretical uncertainty of measurement of O is given by this formula. Okay. Yeah. Good. It is easy to show that the expectant value of O if the system is in state psi is given by the scalar product of psi and O acting on psi. And the variance of O, of the measurement of O, is given by such formula. Yeah, good. Here, up to theoretical uncertainty, delta O psi, the uncertainty of measurement is a matter of experimenter, their methods, their apparatus, etc. Yeah. Once more, up to the theoretical uncertainty. Yeah. The uncertainty of a measurement, yeah, or error of the measurement is the error of the measurement is the matter of experimenter. Good. When quantum mechanics already detected that the theoretical uncertainty of a measurement of an observable is different from zero, then no experimenter with her or his method and apparatus can obtain uncertainty less than the detected value in her or his measurement. The last experiment expression, the last expression of the variant leads to the celebrated Heisenberg uncertainty relation. Then the last, the last expression of the variant delta O C leads to the celebrated Heisenberg uncertainty. So where this is the commutator of O1 and O2. So the commutator of operator is very important in this case. Yeah, it means that to non-commutative observable O1 and O2 cannot be measured simultaneously with zero uncertainties. Even if we get O1, certainly we will not get information on O2, and vice versa. If we get O2, certainly we will not get information, yeah, on O1. it can be shown that two commutative observables have common eigenstate. Therefore, they can be measured simultaneously with zero uncertainty. There are one-to-one correspondence between the set of all closed subset of Hilbert space and the set PH of all orthogonal projection operator in Hilbert space H. The set PH form an orthocomplemented or modular lattice. After spectral theorem of self-adjoint operator, self-adjoint operator O can be written formally as this integral, and where A is a projection value measure or spectral. Good. Therefore, an observable can be represented as an orthogonal projection value measure. Then the expectation value of observable O is given by this formula. Good. Quantum dynamics. There are three descriptions of quantum dynamics. Yeah, the first one is Schrödinger Lagrangian description. Yeah, the solution of the above Schrödinger equation will, with initial value, say psi 0 is equal to psi 0, can be regarded as the action of the dynamics group R, plus on the Hilbert space. This is the action of R on it, describing the dynamics of the system. Yeah, good. In Heisenberg Alien description, yeah, we have this equation, yeah, describing the Heisenberg's dynamics in quantum mechanics. Yeah, the dynamics, the evolution of the operator of the observable. Yeah, the solution of the above Heisenberg equation with initial value OH, yeah, can be regarded as an action on the dynamics groups R, plus on the set SH, yeah, of all self-adjoint operators in the Hilbert space H. So there are the rate of change of expectance value of observable O is given by this equation. Yeah, Yeah, the Hamiltonian operator H reflects the whole quantum system. Therefore, a quantum system is a pair H, H, yeah, where consisting of separable infinite dimensional complex Hilbert space H and a particular self-adjoint operator H in the Hilbert space. Yeah, the operator H, yeah, represents Hamiltonian function. Yeah, or total energy of the system. Yeah, the total energy of the system reflects the system. Yeah, good. So comparing the rate of change of the expectation value of quantum observable O, yeah, with the rate of change of a classical observable A, yeah, Dirac came to the idea of canonical quantization. It means how to find the quantum counterpart of a classical observable. Given a classical observable A, for example, then what is the counterpart of A in a quantum description of the system? So it then lead to another more general quantization methods. For example, the geometric quantization, yeah, the geometric quantization is a quantization method, yeah, stem from this canonical quantization, yeah, and now quantization is understood as how to change or how to get quantum words from classical words. This does not only concern classical mechanics into quantum mechanics, but also in quantum fields, classical field into quantum fields. For example, in the case of gravitation theory, for example, yeah, gravity, yeah, Einstein gravity is regarded as field theory, classical field theory, and Now we try to find how to quantize, quantize the field, the gravity, in the field of gravitation, in the context of Einstein gravitation. It is hard to get there. Okay, I think this is this the last slide of my presentation. Good, thank you very much.
Okay. Thank you very much, Mr. Rashid. And I think before this lecture series, I talked to some people, and we have a conjecture. Mr. Fahrani's area is very mathematics, and I think that's proven today, because there are some abstract mathematics that he used in his area. Okay, because we have limited time, and we go to the Q&A session. And there is one question from Zoom, and there is no question from YouTube. So I think I will read the question. This one is from Bang Juanda Klana Putra. What is the relationship between mechanical quantums with on space and time, and also with the structure of the universe? Thank you very much. So the relationship between mechanical quantums with on space and time, and also the structure of universe. Maybe.
Okay. Yeah. Yeah. Yes. Okay. I would like must I answer this question now? Hello. Hello. Ya.
Ya langsung aja Pak Rashid mungkin. Halo.
Oke, Bang Juana ya. Jadi, what is the relation between quantum mechanics in space times, ya, and space time structure? Yeah. Okay. What I have explained here is non-relativistic quantum mechanics. Yeah? Non-relativistic quantum. Well, when relativity, special relativity of space-time does not involve, is not involved in this consideration. Yeah. So when the relativistic effects, yeah, involved in this conception, then we get there the relativistic quantum mechanics, where Dirac equation or Klein-Gordon equations, yeah, control the dynamics of quantum system. So then, when the space-time structure, yeah, is flat, it's not flat, yeah, curve in curve space-time structure in space-time, yeah, we have formulate another kind of quantum mechanics, yeah. So and what is the relation between quantum mechanics formulated in space-time, yeah, curve space-time, I think, yeah, and the time structure, yeah. So it is another kind, yeah. It is different, yeah. It's different, yeah. So in the first case, yeah, quantum mechanics in curve space-time means that space-time is regarded as backgrounds, yeah, of the system, yeah. So the system is not, yeah, is regarded.
Okay.
does not influence the time space-time structure. Yeah? But when we speak about the time space-time structure, and then this another kind of theory. Yeah? In quantum gravity, for example, we try to quantize the gravitation. Yeah, and the field of the gravitation field, we try to quantize the gravitational field. Yeah.
Okay.
To quantize the space-time. Yeah. In the case of quantum mechanics in space-time, in smooth space-time, once more, yeah, space-time is regarded as a background, yeah, of the system. And in the second one, yeah, we try to quantize, yeah, the space-time. Yeah, it is different. Okay.
Okay.
Good. So.
Okay. Okay. Yeah. Thank you for the answer. I think because of the time constraint, we only have one more question. So the next one is from Saisnan from Ukraine. Can we extend the mathematical formulation, or maybe state space, observable algebra, etc., for quantum mechanics in open system? Regarding the dynamics in the open system might be dissipative, is related to non-Hermitian operator.
Okay. Okay. Yeah. Yeah. Yes, we can. Yeah. Maybe you have heard about the operational quantum mechanics. Yeah. Operational quantum mechanics. Yeah. This kind of quantum mechanics implemented in the case measurement theory. Yeah. Quantum measurement theory. So I have in the last, sorry, not in the last, yeah, but in my slide, yeah, I explain about the representation, yeah, projection value measure, yeah, representation of quantum observable. Yeah, if we exchange, yeah, if we generalize, yeah, generalize the projection value measure to positive operator value measure, then we have a more general, yeah, quantum, more general quantum observable. Yeah, it's not a self-adjoint operator. Yeah, okay. This is the one example of such generalization, yeah, of some extension of the mathematical structure in quantum mechanics. Another case, yeah, another example is when we, yeah, when we, for example, yeah, when we the field complex, yeah, field in Hilbert space, yeah, we can generalize it in the field with two quaternion. I'm sorry, yeah, quaternion, yeah, the quaternion Hilbert space when we change the Hilbert space, yeah, with complex Hilbert space with quaternionic Hilbert space, then we have more general quantum mechanics. Okay, so there are so many possibilities to extend the mathematical structure in quantum mechanics, then to get a more general quantum mechanics, yeah, that's accommodate such need, yeah, to in describing a more general system, yeah, physical system. Okay, this is what.
Okay, yeah, I think that's all for the questions and the answer. Thank you very much, Mr. Roshid, for answering all questions. And thank you also for sharing with us a lot of things today. And yeah, it's good to have collaborations between mathematics and physics. Okay. And let me introduce the speaker for the second session. Okay. So for the second session will be delivered by Mr. Alexander Jimena Balsomo, PhD. He is an associate professor at West Visayas State University, Filipinas, and he got his bachelor and master from University of the Philippines, Visayas, and the PhD from Ateneo de Manila University, Quezon City, Philippines. And the interesting thing here is he got his master from education, then go back to, yeah, this one is some pure mathematics. And his research interest is related to mathematical foundations of quantum mechanics and also population dynamics. Okay, no need to prolong the introduction. Please, for Mr. Alex.
Thank you very much, Uva, for the introduction. So quickly, this will be my title. And thank you for the invitation as well for today's talk. This will be the title of my presentation, somehow adapted from the article written by two physicists, Hirschfeld and Helsender, on the deformation quantization in the teaching of quantum mechanics. So we'll just rename this as teaching of Lie group representation. My collaborator, this is a joint work with Job Nable. He's currently watching with us in Zoom currently. So this will be the outline of my talk. So I will just quickly talk about classical mechanics and quantum mechanics because Professor Rosid was able to really explicitly explain to us these two. So I'll just do the outline and quick review on this. But my main presentation was on the relationship of these ideas to deformation quantization and as well as representation theory. And I'll provide two examples on how to compute or construct a representation of these two groups, the Euclidean motion group and the similitude group. And then at the end, there are some items or questions that might be still open for us to work on for those who are interested in this topic. So let me show you a picture of when I was in Yogyakarta. Uha was as well there in this seminar on representation theory. That was in 2015 when I was still taking my PhD in Ateneo de Manila. And this seminar somehow helped me understand what representation theories really is. So now, some quick historical outline. So if for a standard study of representation theory, normally we start with finite representation theory. These ideas came from these mathematicians, Weber, Frobenius, and some other mathematicians such as Burnside, Schur, and Mollien. However, when this idea would be extended to Lie group representations or topological groups, somehow it's not that smooth because of the difficulty. However, because of some tools that emerges in the 1900s, such as the Lebesgue integral and the square integrable spaces, such as the L2 space, the development of unitary representation theory, it's actually inspired by the discovery of quantum mechanics. In this period, this is the golden age of the new quantum mechanics. So, and as mentioned earlier by Professor Rosid, he mentioned these names who are influential in the development of quantum mechanics, and von Neumann was able to solidify the mathematical foundation of the new quantum mechanics. And the connection of groups with quantum mechanics was actually studied by Vial and Wigner in 1927. So I'll refer you to the to this historical survey written by George Mackey. He's actually the one. Mackey is the author of the induced representation. This is a method of construction of representations from groups. So now, a quick overview, what is classical mechanics, quantum mechanics, since this was already explained earlier. So quantum mechanics, the model is explained by the space of observables, which are smooth functions on the symplectic manifold or a much bigger Poisson manifold with some structure. In this case, for the symplectic manifold, we have the symplectic form. So the collection of all of these observables together with these two structures, the ordinary multiplication of functions and as well as the Poisson bracket will give rise to a Lie algebra of observables. On the other hand, when we are talking about quantum mechanics, as explained as well earlier, these are modeled by self-adjoint operators on a Hilbert space. In this case, for example, we have L2 on the in the even-dimensional Euclidean space, and collect all of these operators together with these two structures, the operator composition and commutator bracket would give rise to a Lie algebra structure. So now, if we put all of these side by side together, classical mechanics and quantum mechanics, as mathematicians, although these two mechanical systems are different to each other, but the structures are actually similar. These are Lie algebra structures. So as mathematicians, we are interested with the connection between this structure, classical mechanics, and another structure, quantum mechanics, by some function or some map. In this case, we are looking at a linear map to preserves these structures. So we now look at what we call with quantizing observables from classical mechanics, which are differentiable functions or smooth functions, to operators. So to begin with the basic way to do this, the canonical quantization, we only look at the span of the coordinates of these spaces. In this case, we are interested with polynomials. For example, in this case, we let our n to be equal to 1, meaning we will be working on the two-dimensional Euclidean space, where our Hilbert space will be in L2. So we look at on the span of these polynomials. These are the basis elements of at most degree 2, and then try to compute what are the corresponding operators on the L2 space. So this is actually known in quantization literature or in physics literature. But the question later is that we want to look at, can we extend not only on this span of finite basis element, can we just simply extend this to the whole space of differentiable functions? But this construction of this canonical quantization of these coordinates is derived from the Schrödinger-Vial representation. And this is actually the representation of the Jacobi group. So as let me see, and this is the group. This is the Jacobi group. So it has a Lie algebra, and the Lie algebra representation of this group will give rise to this canonical quantization as shown earlier. However, as I mentioned earlier, that can we somehow extend from these basis elements of polynomials to the whole space of differentiable functions? But according to Groenewald and Van Holt, it says no, we cannot extend this if this will be our quantization method. So we define quickly what is quantization. So as I mentioned, quantization is just a correspondence between classical observables to quantum observables. So at this time, I'm only looking at quantum observables as operators on a Hilbert space. It must satisfy these two conditions, that it preserves the multiplication and the commutator bracket as well. But as mentioned earlier by Professor Rossi, that classical mechanics is a limiting case of quantum mechanics, as well pointed this out by Paul Dirac in his work in The Principles of Quantum Mechanics. It's a good book to read for those who are interested in studying quantum mechanics. So there are three quantization groups of quantization methodology, at least three. One is the Hilbert space quantization, as mentioned earlier by Professor Eurosid. We have the geometric quantization, and the other one is the path integral quantization by Richard Feynman. But my main concern today is to discuss, to talk about deformation quantization. So first, what is deformation quantization? According to these authors, Bayan, Flato, Fronsdal, Norwich, and Stornheimer, let me quickly quote these statements from them. The usual probabilistic interpretation of quantum mechanics contrasts with the deterministic character of the classical mechanics. You will see later from our particular examples. However, the suggestion is, we suggest that quantization be understood as the deformation of structure of algebra of classical observables, rather than as a radical change in the nature of observables. So imagine you want to associate a function to an operator. It's really a big change. But their suggestion, what if we simply deform classical mechanics to be quantum mechanics? So how was this done? So let me quickly look at some of the known works by some of those who work on the foundations of quantum mechanics. Hermann Vial wrote this quantization formula. This is an operator on functions on the Schwarz space, or rapidly decreasing functions. And if we will try to simplify this operator above, this is the form of the operator. The sigma here represents a differentiable function, and let's call this to be our symbol. So therefore, this is W sub sigma is just the operator associated to this symbol sigma. So this will be our operator, but try to look at the components of these operators. The first component here, this is just the Fourier transform of your function sigma, which can be expressed this way on R2n. On the other hand, this exponential expression e raised to I uq plus vp, it's actually an operator from the Schrödinger representation, where p is the momentum operator and q is the position operator. So take note, these two operators can be as well written on the examples that we will be having later with the Euclidean motion group. So now, from this operator by Vial, we look at another expression from Eugene Wigner in 1931, and he considered this function. And this function can be somehow written in terms of the bracket notation, which is many physicists are familiar with how they write this bracket notation. And let's try to look at the properties of this function, which is called now the Wigner function. This Wigner function is actually a quasi probability distribution. So in other words, it's a probability distribution that allows negative values. So however, what is interested with the Wigner function is its association with the Vial quantization or Vial operator, which I was able to show earlier. In the expression here below, if you have noticed the right-hand side is simply the usual expectation value of a function of a random variable, where we allow this expression, our Wigner function, to be our probability distribution. How about the left-hand side? The left-hand side actually is an expression of an expectation value of an operator. In this case, our operator is actually this A hat. So connecting all of these, this theorem tells us that the expected value of the operator, say in this case, the Vial operator, is actually the expected value of the function associated to this Vial operator. So now we can see the connection between Vial operator and Wigner function. But Moyal and Groenewald, in these two different literatures and papers, was able to show that the Wigner function and the Vial operator and the Wigner function are actually inverse of one with the other. So in other words, if these are inverse functions or inverse expressions one with another, so therefore, what is the composition of two Vial operators? And what is the symbol associated to this Vial operator? So let us show this here. The composition of two Vial operators has a function which is expressed as the product of these two functions, F star product G. And since your Vial operator has an inverse, so therefore we can write this as the star product of the function F and G as defined this way. So it has properties. The product has the following properties. So we'll just simply look at this: associativity, classical, semi-classical limit, and property of the unit. And as well as if we compute these functions on the Schwarz space of functions on the even-dimensional Euclidean space, we can have this formula. On the other hand, there's also a summation formula written this way on the space of differentiable function. So in other words, rather than working on operators, we can now describe quantum mechanics as the space of functions with some additional expression of in this case, we have the Planck's constant, and the operators that we are now considering are the star product and this commutator bracket in terms of the star product. But this star product is defined on the flat Euclidean space. So if we define the star product in general, so this is defined as follows. This is just the sum of these expressions where the new expression here is a parameter, while your C raised to R expression here are your bidifferential operators with these properties. And these are some of the properties that you can consider from this star product, that this is the deformed multiplication. It has the non-commutative property. If you can remember that operators in terms of the mapping composition is not commutative, so it follows the same property of non-commutativity, and you have the deformed Poisson bracket, and as well as the identity properties. So now, so our interest is that for this talk, our interest is what is the connection between quantization and representation theory? In particular, in this case, it's the unitary representation theory. So according to these items, you can see that quantization as a quantization theory, it is inevitable that deformation quantization found use in the representation theory of Lie groups. And according to Bayan and his co-workers, they are confident that the star product have a promising future in representation theory. So a quick review of representation theory. So I'll not delve with the definition of group and the vector space. This is actually the slides I've also already presented with my previous presentations as well. And the Lie group, it's simply a group, at the same time a manifold whose multiplication and inversions are smooth maps. So the examples of Lie groups, finite dimensional Lie groups, are actually your generalized matrices, general linear matrices. which are, for example, you have your SO2 and this semi-direct product, or every closed subgroup of your GLN. Okay, so on the other hand, Lie algebra, it's a vector space over a field together with this Lie bracket, which has these properties. And an example in terms of finite dimensions, so you have this n by n space of n by n matrices. Therefore, it's a vector space, so you can identify the basis elements. For example, given these space of matrices, the SO2 and SO2 with R2. So what's the connection between Lie groups and Lie algebra? If you take the exponential map between the Lie algebra to the Lie group with this definition, so therefore you can compute what's the corresponding Lie group to a Lie algebra. Well, Lie's third theorem will always tells us in terms of matrices, we will always have a corresponding Lie algebra to a Lie group. For example, if you compute the exponential of this matrix would lead you to this one parameter subgroup of matrices of this Lie algebra on SO2. So now, these are some of the examples of computations, connections between Lie algebra and Lie groups. So we are interested with representation. So in this case, as you can now see, the definition of a unitary representation. So therefore, it is a homomorphism of a group with a group of operators. In this case, we have unitary operators. So sorry, this must be unitary operators. When you're dealing with Lie group, so therefore, this map must be smooth. But in general, if you're dealing with topological groups, you're dealing with strongly continuous function in this case. So these are unitary representations. For example, we will be working on the Euclidean motion group. The unitary representation are defined by these operators of this form. So on the other hand, in terms when n is equal to 2, specifically for lower dimension Euclidean motion group or Euclidean motion group on the two-dimensional Euclidean space, this is defined by these operators, or we can express these operators in terms of the one parameter subgroups. So, on the other hand, we can as well express the unitary representation of this group as follows. If we rewrite our operators earlier, we can abbreviate these as Q and P, where Q is of this form, and we will call this to be our position operator, while your P, well, this is just a Taylor series expansion of this translation of the function. So we will just call this to be our momentum operator, which is similarly written as the Schrödinger representation, which I was able to show earlier. So in this, in standard unitary representation, if you group together, if you collect together all of the unitary representations, you can classify these representations into two representations are said to be equivalent if they satisfy these things. Okay, so on the other hand, since we have Lie groups and we have Lie algebra, we can compute a Lie algebra representation from the Lie algebra to the Lie algebra of operators by simply taking this derivative. Although we can define separately the Lie algebra homomorphism or Lie algebra representations, but because of the connection of the exponential map, we can simply take this derivative. So in other words, these are some of the things that we need to learn about Lie algebra representations, that these are on the space of smooth vectors, such as the Schwarz space, and it preserves the Lie bracket structures of both of these Lie algebras. And as well as this is Q immersion. Once you multiply a plus or minus I to this becomes self-adjoint, which is important with the canonical quantization, which I have shown you earlier. So, for example, in this case, if we go back to our unitary representation of the Euclidean motion group, we can compute for the Lie algebra representation of this group or representation of the Lie algebra of your M2, and this can be shown, and this will be the computations. This is the operators that defines the Lie algebra representation of the Euclidean motion group, or you can as well look at this in terms of the basis of M2, so which you can express with these three operators. So, question. So, what is now the program that we are working on? The program is given a star product. If we know the star product on these functions, so the question, what's its association with the unitary representations? So in this case, this will be the program of this research. So first is to look at the co-adjoint orbit of the group, meaning what is the symplectic manifold associated to a group. So this is defined by this action or co-adjoint action of your group to its dual. The dual is just a linear functional on the dual of the Lie algebra of your group. And once you can identify this co-adjoint orbit on the group, then identify what's the appropriate coordinate system or charge on this symplectic manifold. Oh, I forgot to mention that co-adjoint orbits are actually symplectic manifolds. It's Kirillov was able to show that. And once we identify the coordinate system of these symplectic manifold, then we look at what are the Hamiltonian functions, what's the Hamiltonian vector field, and what's the Kirillov symplectic form of this co-adjoint orbit. Then we are to show that given that coordinate system on the symplectic manifold, this is the most important part of the program, that is to show that your star product is covariant, meaning it preserves the Lie algebra structure given you have the Poisson bracket and the commutator bracket in terms of your star product. For you to identify that these operators are actually the operators that defines your Lie algebra representation. And you can easily show that this is indeed a Lie algebra representation coming from this equality. Now, once you know what's your you have a covariant star product, then compute for the Fourier transformed operators instead of working on that operator. Then after the computation, verify that indeed it is the unitary representation that is associated to the group. In other words, in this computation, we already have the idea what is already our unitary representation. And if it satisfies this Cauchy problem, then it is indeed the unitary representation of the group. But if the group is already simply connected, then right away, the exponentiation of these operators will already give rise to a unitary representation. So in this case, let me quickly run through the computations for both groups, the Euclidean motion group and the similitude group. So in this computation for the Euclidean motion group, the co-adjoint orbit are simply infinite cylinders with actually parameterized by this radius of the cylinder. So the coordinate system that we can identify is, of course, the cylindrical coordinate system, then apply this coordinate to our Hamiltonian system. Therefore, you can compute all of these so that using your Hamiltonian function as shown here, you can right away compute for your Lie algebra representation. But first, you have to verify that indeed it satisfies the covariant property of the product. In this case, we utilize the Moyal star product. So further computation would give you right away, this is a bit tedious to do this computation, but you will be able to come up with these operators. And this operator, if we will go back from our earlier slides, you will see and you will notice that this is exactly the same operators that defines the Lie algebra representation of the Euclidean motion group. But we can make use of the Cauchy problem, which we have presented earlier. So therefore, we can conclude that indeed, that these operators will define as our unitary representation of M2. But the question is, can we extend this to higher dimension? Well, the answer is yes. In this case, for M3, we have submitted a paper for this, and we're waiting for the result. And for the generalization, we were able to do the computation. There are some problems regarding with how to from a localized operator, how can we globalize the said operator? But can we extend it to any Lie group? Maybe, because we have to satisfy the covariance property. So maybe later, this can be a question that we would ask: how can we relax this condition for us to accommodate more groups? So moreover, when we're dealing with looking for the space of functions to where your unitary representations will be invariant with, or that makes your unitary representation irreducible, authors have already recommended what you call star polarization, which is equivalent to the polarization which is known in geometric quantization. And if we already as well know that the space of functions that we are working with are simply connected, then therefore we can globalize the operators right away because of the monodromy theorem. However, the problem is that what if your space of functions is not defined on a simply connected manifold? Now, how about for similitude group? Okay, quickly, let me show this to you. If you have noticed, the title is not a unitary representation of the similitude group, because the answer is we cannot derive the unitary representation, only the Lie algebra representation. Well, the first thing is that the similitude group, it's not simply connected. And the second, when we use the Cauchy problem, it is a Lie algebra representation of a different representation, but not on the unitary representation. This is the main difference of a Euclidean motion with the similitude group, is this dilation expression lambda. This is just expressed as a in the Lie algebra as the identity matrix. So these are the commutator relations of the basis elements of the Lie algebra of the similitude group, which actually what's nice on computing this Lie algebra representation is that we can derive these two Lie algebra representation. The first one was already computed by Jep and Hai much earlier. And this one we already computed this a few years ago. But this similitude group will give us these two. Okay, let me quickly show this to you. This is the co-adjoint orbit, and the computation of the co-adjoint orbit is this. And what is this? This is just actually this space. This is the cotangent bundle of a punctured Euclidean plane. Meaning, try to imagine you have a two-dimensional Euclidean plane punctured in the middle at the origin, and then each of the point has a Euclidean, two-dimensional Euclidean space. That's the cotangent bundle of the punctured Euclidean space. And this is topologically homomorphic with our group. Now, moreover, the coordinate system and the Hamiltonian system of these expressions are as follows. We generalize the use of the cylindrical coordinate system on this space. This is still the cylindrical coordinate system, except for the tangent space x and y with coordinates x and y, and the Hamiltonian function is of this form. Okay, and the Kirillov symplectic form from this information will give rise to this symplectic form, as you can see in the screen. And the Moyal star product one nice thing about the Moynihan-Stahl product are the matrix entries of the symplectic form, which we can substitute from this matrix representation to our Moynihan-Stahl product. And once we substitute these things, we can compute for the covariance. We can verify the covariance of this star product. Then this operator is the Lie algebra representation because of the covariance property. Then again, compute for the Fourier transform version of your operators, and this is the shortened computation. However, because the computation would be difficult if we're dealing with 4 variables, but you will notice later that we can cut these variables in from 4 variables to 2 variables. That's actually can be verified by the method of star polarization. And this would lead us to this operator. And this operator will now define the Lie algebra representation of our similitude group. But from that, or from this, we can as well derive the other Lie algebra representation operators of the other 2 groups, which I mentioned earlier, the Euclidean motion group, which is represented, this is the associated Lie algebra, and as well as the affine group on the real line. So the question is, if we exponentiate this operator, can we give us the unitary operator? The answer is no. It will not satisfy what that unitary representation is, because the unitary representation of the similitude group is, there's only one unitary representation, which is defined by this operator. But our computed Lie algebra representation will give rise to this operator after the exponentiation, or after satisfying the Cauchy problem, which is not a unitary operator, but simply a representation of our similitude group. So for future directions of this work, I'm currently working on low-dimensional Lie groups. I was working with the affine Poincaré group, which is instead of the rotations on the Euclidean motion group, I was looking for the hyperbolic matrices as a substitute to those rotations. But as well as I'm working with computing the opposite of this program, which is given a Lie algebra or a unitary representation. Can we come up with star products, meaning on these groups, such as semi-direct products, the coadjuvant orbit of that semi-direct product of a Lie group and its dual. Also, possible projects with students in the future are as follows: the generalization of this construction, which is, I believe, difficult to do this because mostly the work in physics are specific to a particular group. For mathematicians, we are more interested on generalizing. In some applications, recently I was looking for the Kepler problem on the hydrogen, because there are some other expressions on the Hamiltonian system that would lead us to such computation. And of course, lastly, will be the uncertainty principles of the Lie groups, looking at these computation and the connection of the star products on these computations. So the next speakers on the following months will be on the representation, from representations to star products, will be given by Arnie and Francis, who are currently watching with us right now. So this is my group in the Philippines working on this topic. I believe they are here now. This is watching in YouTube. So this is our supervisor, Job, is currently with us here. So again, thank you very much. Terima kasih.
Okay, thank you very much, Mr. Alex, for sharing with us. And as we know, like Lie representations are very hot in mathematics. Okay, so as mentioned by Mr. Alex earlier in the beginning, so we met at the first time during Sim School 2015, and at that time I was very new, becoming a lecturer at Universitas Gadjah Mada. Okay, no need to prolong. I think we can continue to Q&A sessions. So there is no question from YouTube, but there are 2 questions from chat box. I think we go from the first one first. So from Mr. Aziz from UGM, can we use the idea of mathematical quantization of classical mechanics to quantize the classical field theory? Okay, please.
So far, I'm not familiar with the classical field theory, even the quantum field theory. But what is the a big idea about these things? The computation is dependent on the symmetry where on what manifold we're working on. For example, the early quantum mechanics that physicists have been working on are on the flat space, which is dictated by the symmetry of the Heisenberg group. So for mathematicians, we look at what if we have different space of manifolds that we are working with. So we also look at with other groups as symmetries. So in this case, on the idea of this quantization of classical mechanics to quantize, well, one nice thing about different deformation quantization, it has already overcome the problem on the no-go theorem by Groenhold and Van Hove. So I believe, yes, it can. It can.
Okay, so he believes that he can. Okay, thank you very much. And for the second question from Mr. Edi Kurniadi, have you already constructed IUR or SIM2 using the orbit method introduced Kirillov? If yes, how about the intertwining operator for this IURS? Thank you.
Oh, very good question. Thank you very much. I have not. I'm not familiar on how to. This is geometric quantization. Although Kirillov, for example, has good books, or like, for example, lectures on the orbit method and have examples on that. But I haven't tried yet. But it's a good suggestion so that I could compare the difference. And however, I tried the induced representation by Mackey and was able to come up with the same representation, which is actually the usual method that they normally use. So again, in terms of the orbit method, I haven't used this yet.
Okay. Okay. Maybe for Mr. Eddie, any further questions? If yes, then you can turn on your microphone also, if you would like to.
Okay, thank you very much for the time. I have already gave the chat about my questions. Okay, this is very nice presentation for me about the representation theory. And actually, I study the representation theory of Lie group, but in my work, I use the orbit method. So for example of your presentation that you compute the irreducible unitary representation of similitude group of SIM2, okay, you use a quantization, but in my case, I already found the irreducible unitary representation of this group using the orbit method. Maybe just share, we can work together how to find the intervening operator of your work in this representation theory. This is very nice for me if you have a time for discussing about this result. Thank you.
Thank you, Eddie. I think with the literature so far, like particularly in wavelets and coherent states, which normally these groups are being used, they usually they mention, and so far with my computations using induced representation, it would only come up with a single representation. Unlike with the Euclidean motion group, you can have infinitely many irreducible unitary representations for this. But yes, it's very nice to work with you in order to find these things.
Maybe for the next question, so maybe we can also investigate how about the properties of this representation. For example, is this representation is square integrable representation?
In literature, yes, it is. It is
Yeah.
a square integrable representation.
So we found the same calculation maybe. So
yes,
maybe we can determine about the intervening operator for this. Okay, thank you.
Yes, true. Thank you very much.
Okay, it's very interesting discussion. Hopefully you can do some further collaborations. Okay, I think that's all for our main agenda for today. And once again, thank you so much for Dr. Fahrani Rashid and also Mr. Alex. And we arrive in our last agenda for today. There are several announcements from the chair of organizing committee. So for Professor Indah Emilia Wijayanti, please.
Thank you very much, Uha. So good morning, and thank you very much for the speakers for the nice talk, beautiful presentation. I think we learned many things here from algebra side or mathematical side. And as you know, maybe this is a series, so we have next lecture in July. I think in 24th, yeah, Uhaya, 24th July, and also in August. So please keep in touch with us and join our next lectures. Yes, thank you very much for all, for the participants, for the organizer, for Pak Nanang from Indo MS, and for Pak Fajar for Department of Mathematics. Thank you very much. And see you in the next lecture. Yeah, I hope we will meet again virtually, and maybe we can arrange the more fruitful discussion in the next session. Thank you very much, Uha. Your time is yours.
Okay, thank you very much, Professor Indah. And yeah, I would like to remind you once more. So we have 3 programs for our lecture series. So for the second one will be next month. And yeah, just keep in touch and we will share the announcement later. Okay, I think that's all for our agenda today. Thank you very much for joining us. And yeah, we are sorry if we have some mistakes, and see you in the next lecture. Wassalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone.
Bye-bye.
Thank you.
Thank you.
Bye, everybody.
Thank you very much for all. Thank you.
Thank you. Thank you.
Thank you, Mr. Alex.
Thank you very much.
Thank you very much. It's a great pleasure. Thank you.
Okay, thank you, everyone. I will close from the host. Keep healthy and stay safe.
Matur nuwun, Pak Rashid. Mohon maaf tadi sempat disconnect saya.
Ini saya tutup dari sini, ya, Bapak Ibu.
Terima kasih, Nana.
Okay, have a good weekend.
Assalamualaikum.